All right, welcome to Codex. Today we'll be hearing from Professor Pete Casazza. Pete is a Curator's Distinguished Professor at the University of Missouri and the Director of the Frame Research Center. Over the past few decades, his research has developed the foundations of frame theory. In this time, Professor Casazza led several influential research programs in the community, including frame theoretic approaches to phase retrieval and to the Caddiston-Singer problem. Pete has found notoriety not only in math circles, but also in his local animal-loving community. Over the years, he has taken on dozens of homeless bunnies from the local animal shelter and provided them a life of luxury. So just yesterday, Pete turned 75 years old. And for his birthday, he's going to talk to us about two distant sets. Take it away.
Okay. This is a paper with Teen Tron, my PhD student who just graduated. He's going to Florida International University as a postdoc, and my wife, Janet Tremaine. I think this may have already appeared in JFAA. Uh-oh, this guy didn't want to change pages. Now we got a problem.
Maybe click on the PDF first. Click on it and then press over. It might not be highlighted as the active app.
I can't get at the PDF. There we go. Click on the PDF. Quit it.
And now try the arrows.
There we go. Thank you.
No problem.
Anyway, that's just giving NSF some credit. Okay, the definition. Set X in Euclidean space Rn is a two-distance set if there are two numbers A and B such that the distances between any pairs of points are either A or B. If a two-distance set X lies on the unit sphere, then it's called, shoot, I changed this morning. This was a misprint, shoot. I actually clicked on the old PDF, it doesn't matter. This was supposed to be blue spherical two-distance sets. Sometimes when they give the definition, A can't be minus B. That is, A and B have to be completely distinct in modulus, although not everybody does that. The point is that a set of vectors in an n-dimensional Euclidean space is a spherical two-distance set if there's two real numbers, alpha and beta, lying between -1 and 1, such that the inner product of any two vectors are either alpha or beta. And we'll call alpha or beta the angles of X. So the thing we have to be careful about here is almost always when we start talking about the inner products of two vectors in frame theory, we almost always talk about the absolute value of the inner product. So it's important to notice here, this is not the absolute value. This is the actual inner product. If we took the absolute value, this would become a four-distance set because it would be plus or minus alpha and plus or minus beta. So alpha and beta are going to be the angles of this two-distance set. And of course, a frame xi is, I should also say, the definition doesn't require these to span. That is, it doesn't require the vectors to be a frame. A frame for xi is equiangular if there's an alpha so that the absolute value of xi, xj equals alpha for all I unequal to j. So for some people, this would be a two-distance set because xi, xj is plus or minus alpha. For others, this would not be a two-distance set because they don't allow you to use plus or minus alpha. Something that was worked on for a very long time was the maximum size of a spherical two-distance set of distinct vectors in Rn. This has been a classical problem in distance geometry for quite a while. Just recently, it was resolved. So it will denote by G of n the maximal size of the two-distance set in Rn. And I don't know how to pronounce this person's name, Glazerin and you. They proved that G of n is n plus 1 over 2 for all n greater than or equal to 7. Now, for people who work in equiangular frames, it's known that in the real case, this is the upper bound on the number of vectors in a equiangular frame. There is an exception to this rule. It's true for all n greater than or equal to 7 as long as n is not the square of an odd integer minus 3 for any k and n. So this at least gives us an upper bound. Unfortunately, I think I didn't put in here that you can actually reach this. And the trouble is, I now realize it's in some earlier research of mine, and I don't think it's in this paper, so I may not have said it, but you can actually reach this bound every time. If we have a spherical two-distance set in Rn, remember spherical just means the vectors are norm 1, at angles alpha and beta, for each I, we'll let I sub I alpha be all the j's for which xi, xj is alpha. I sub I beta will be the set of all j's for which xi, xj is beta. So it's clear that if you take the absolute value of I sub I alpha plus the absolute value of I sub I beta, you're going to have m minus 1. Because remember, these vectors are norm 1. So when we're talking about the inner product of xi, xj, yeah, this means I made a mistake here. When I said xi, xj is alpha, I should have reminded you I is not equal to j. If I equals j, these are norm 1 vectors. xi is 1 every time. In general, the cardinality of these sets depend on I. That is, different i's will have a different I sub I alpha and I sub I beta, whatever. When they're independent of I, then we'll say this set is regular. So a regular set means for every I, the number of j's for which xi, xj is alpha will be the same for every I. A spherical two-distance set at angles alpha and beta is said to be regular if the cardinality of the set I sub I alpha and hence the set I sub I beta does not depend on I. This is just a slightly more formal statement of what I put at the end of the last page. We'll call k sub alpha the absolute value of I sub I alpha and k sub beta the absolute value of I sub I beta in this case, which means these don't depend on I, so we can ignore the I. The Graham matrix of a frame is, of course, the matrix xi inner product with xj, taken overall I and j, going from 1 to m. And a spherical two-distance set is regular if and only if its Graham matrix has constant row sum. So this is kind of a simple way to check if a two-distance set is regular. Just write out its Graham matrix and look at the row sums. In this case, we'll call this common number the Grahamian constant of x. A family of vectors is said to be a frame. Oh, probably everybody here knows the definition of a frame, but I'm not going to spend a lot of time on this. I think there's one page where it's just defined. If for all x and Rn, there's constants A and B positive, A times the norm of x squared is smaller than the sum of x xi squared is smaller than b times the norm of x squared. The only thing we need to know here is A and B are the lower and upper frame bounds respectively. What we care about is the frame is an A tight frame if A equals B, and a Parseval frame if A equals B equals 1. It's well known that X is a frame if and only if it spans the space. As long as it spans the space, these inequalities here certainly have to be satisfied. Given a frame, I'm not sure we use the synthesis operator, but anyway, the synthesis operator, we usually just also denote by X by turning it into a matrix. It's the M by M matrix whose jth column is X sub j. So the synthesis operator will just take all the frame vectors, make them column vectors in an M by M matrix. The adjoint is called the analysis operator, and the frame operator of X is S equals X, X star. So the frame operator S of X looks like the sum of X, Xi, Xi. X is an A-type frame if and only if its frame operator is a multiple of the identity, namely S equals A times I. So X is an A-type frame as long as it satisfies this reconstruction formula. A times X is the sum of X, Xi, Xi for all X. When all the A-type frame vectors are unit norm, then it's actually known what the constant A is. It has to be M over N. And of course, X star X is the Graham matrix of X, which is different from XX star, which is the frame operator. Thickest, I probably should have put this in here, that, well, I think it's on the next page. Suppose Xi is a collection of vectors in Rn. The frame potential is the quantity, the sum over all I and j of the absolute value of Xi Xj squared. This was introduced by Benedetto and Ficus, and I think I stayed on the next page. No, I didn't. I stole their result. Anyway, frame potential introduced by Benedetto and Ficus. They essentially proved this result. If I had a set of unit norm vectors, then the frame potential is always bigger than m squared over n. And we have equality if and only if X is a tight frame. Yeah, I think that's all I'll say about that, actually. If X is a spherical two-distance set and is also a tight frame, then we'll call X a two-distance tight frame. Okay, so this is actually the group we're going to study, two-distance tight frames. An immediate consequence of this theorem for the case of regular two-distance sets is if X is a regular two-distance set of M vectors in Rn at angles alpha and beta, and if they have multiplicities, case of alpha, case of beta, then 1 plus case of alpha times alpha squared plus case of beta times base of beta squared is greater than or equal to m over n, with equality if and only if X is a two-distance tight frame. And that's, of course, because what's on the left is basically looking like the frame potential. It's not exactly, but it comes directly from it. So this is, one could think of this as a generalization of frame potential, which is only defined in R2. This holds in Rn for every n, but it's also specialized for regular two-distance sets. A set of vectors is said to be balanced if the sum of Xi equals 0. Now, it turns out that being balanced is a big help for us. A simple characterization of balanced sets is as follows. A set X equal to Xi is balanced if and only if each row of its Graham matrix sums to 0. This is essentially obvious. You actually have to check one little inner product, but so this is the simplest way to tell if a set of vectors is balanced. You check the row of the gram matrix, see if it sums to 0. And that means, of course, also the columns sum to 0. Something we used quite a bit in this paper, which is well known, this is not ours. However, this is the first time I had seen it when we were working here. But suppose xi is any set of non-zero vectors in Rn. If the inner product of every two are negative for I n equal to j, then in fact, you don't have very many vectors. You have n plus 1 at most. And of course, you can have n plus 1 you can have n plus 1 vectors, excuse me, if you take the n plus 1 tight frame in Rn, the simplex. If xi xj is less than or equal to 0 for all I n equal to j, then m is smaller than 2n. So these put certain limits when you're looking at two distance sets, etc., important limits on them. So now we'll give a method to construct balanced, regular two distance sets in one lower dimension from non-balanced ones. As a consequence, we will manage to get conditions for regular two distance sets to be balanced, as well as finding the upper bounds on the maximum size of the sets where both angles are non-negative. So basically where we're going to get to eventually is, in order to have any kind of a decent two distance set, then one angle has to be positive and one has to be negative. If they're both positive or both negatives, they create serious problems for this subject. So suppose xi is a regular two distance set of distinct vectors with its Gramian constant c. This is the sum of the rows of the Gramian. Let alpha and beta be its angles with multiplicities k alpha and k beta respectively. We'll assume that x is not balanced and let p excuse me, be the orthogonal projection onto the span of z, where z is the sum of these vectors. If we let y be I minus p of xi over the norm of I minus p of xi, this is then a regular two distance set of distinct vectors in r to the n minus 1 at the angles m over m minus c times alpha minus c over m, and m over m minus c times beta minus c over m with the same multiplicities. But this set is now also balanced. So we took a regular two distance set. If the sum of the vectors is not 0, we'll just sum them up. We'll project onto the orthogonal complement of that vector. This will produce a new regular two distance set of distinct vectors. And more importantly, this set has become balanced. If xi is a regular two distance tight frame in Rn and x is not balanced, then the set yi constructed in this theorem is a balanced regular two distance tight frame for Rn minus 1. So again, in this case, if we project downwards, we carry all the properties we started with, regular two distance tight frame, and we get to add balanced, where we actually hold on to regular two distance tight frame. And that's well known. If you project a tight frame onto a subspace, it's always a tight frame on the subspace. Let x be a regular two distance set of distinct vectors in Rn. X is balanced if m is bigger than n minus 1 over 2, and n is not one of these offshoot thingies, an odd number squared minus 2. For the case n equals 2k plus 1 squared minus 2 for some k, we actually need m is bigger than n minus 1 times n plus 2 over 2 in order for x to be balanced. Moreover, these sets must have one positive angle and one negative angle. So the point being here, it's sort of saying if you have a regular two distance set if there's enough vectors, it's forced to become balanced. But enough vectors is pretty big, right? We know that the upper bound on the number of vectors is n times n plus 1 over 2. This said, if m is bigger than n minus 1 times n over 2, then this has to become balanced. This theorem, this damn thing, I should have gotten rid of this phone. This theorem gives the upper bound for the cardinalities of non-balanced regular two-distance sets, in particular for such sets with two non-negative angles. So a corollary of the theorem is if xi is the regular two-distance set of distinct vectors in Rn, and they both have negative angles, then we have the following. N can't be one of these unusual cases, an odd number squared minus 2, and m has to be smaller than n minus 1 over n. So the idea is that we know regular two-distance sets can't have any more than n times n plus 1 over 2 vectors. But this is saying if you have two non-negative angles, you have a much smaller upper bound. And once again, you can actually show that this is achieved. And in the case n equals 2k plus 1, an odd integer squared minus 2 for some k, then m has to be smaller than n minus 1 times n plus 2 over 2. And this is also an exact upper bound. So the point being, if you have two non-negative angles, you are much more restricted on how big your set can be. It's going to be much smaller than it could be if you were allowed one positive angle and one negative angle. We're now interested in a case where two distance sets form frames for the space, especially tight frames. The following result will show that we can get frames if the cardinalities of the two distance sets are large enough. If X is a two distance set of m distinct vectors in Rn, then X is a frame if one of the following conditions holds. If m is big enough, it's bigger than n minus 1 times n over 2, and it's not one of these oddball cases, an odd integer squared minus 2. Or if m is bigger than n minus 1 times n plus 2 over 2, and n is not one of these oddball cases. Then in fact, the point is that these are required to span. And it's not necessarily surprising, right? If they don't span Rn, they're sitting in Rn minus 1 or less. And you have a huge number of vectors here. And you just have too many for them to be able to only have two inner products. In the following, we'll give a characterization of two distance tight frames. As a consequence, we'll discover that every two distance tight frame with angles alpha unequal to minus beta always has to be regular. So if we let xi be a two distance frame at angles alpha and beta, the following are equivalent. X is an m over n tight frame for some subset of the integers 1 through m, which span Rn. If I look at alpha times the sum of xj, I didn't actually write this right. Well, j and I sub I alpha plus beta, the sum of x sub j, j and I sub I beta equals m over n minus 1. I actually think I obviously, there's something not right here anyway, because where'd the big J disappear to? this is supposed to be the sum over J and I suppose alpha. Actually, I have the paper here. Maybe I can find it. There's something not right here because the J disappeared. The big J. Yeah, unfortunately, this paper is a year old, which means my memory's not good for that long. Maybe I'll look it up later. If xi is the two-distance type frame for Rn at angles alpha and beta, if alpha is not minus beta, then alpha is already regular. Moreover, the Gramian constant of x is either 0 or m over n. So the Gramian constant of x is either m over n means either the rows sum to 0 or the rows sum to m over n. So if we let P from L2 to Hn be a projection from L2M down to Hn, and EI is the canonical basis of L2N, P of EI is always a Parseval frame, and we call I minus P of EI its Naimark complement. And this was somewhat surprising to me when we found it. If xi is a regular two-distance type frame for Rn at angles alpha and beta with multiplicities k alpha and k beta respectively, then its Naimark complement is also a two-distance type frame for R to the m minus n at angles minus n over m minus n over m minus n alpha minus n over m minus n beta with the same multiplicities. Actually, this is not the theorem that surprised me. I thought something else was coming up. So the main point is regular two-distance type frames carry over perfectly to the Naimark complement. And this puts further restrictions on the types of things that can be two-distance type frames. Yeah, so this is an important result for us. If we have a regular two-distance set in Rn at angles alpha and beta, if m is more than n plus 1, and the Gramian constant of x is either 0 or m over n, then alpha times beta must be negative. So in particular, this covers pretty much all cases for regular two-distance sets. I mean, almost all the time we want m bigger than n plus 1. So this says pretty much in every case, any two-distance type frame must have one negative angle and one non-positive angle, meaning it could be 0. Suppose X is a Parseval frame with the property as Gram matrix has constant row sum. I don't know why I didn't use our notation for that. Then either X or its Naimark complement is balanced. This is the result that surprised me. Even now, intuitively, I don't know where this comes from. We have a Parseval frame with the property that is Gramian matrix has constant row sum. Then either X or its Naimark complement is balanced. That is, the xi's are actually P of EI coming from above. And this says that either the sum of P of EI or the sum of minus P of EI has to be 0. At least intuitively, I never could quite figure out why this is true. Maybe one of you can figure out a logical reason this is true. So if yi is this Naimark complement, then the The sum of xi equals 0 if and only if the sum of yi yj equals 1 for all I. And the sum of, the sum of xi is 0 if and only if the sum of yi yj equals 1 for all I. And the sum of yi is 0 if and only if the sum of xi xj is 1 for all I. So I said I would show some examples. I actually gave up on this. The examples in here are unbelievably complicated, run for pages. The idea was to try to produce infinite families, which we did manage to do, but it took an awful lot of work to produce them. And I decided, if you don't work in this area, it wouldn't make any sense to anybody. Most of these theorems have 5 or 6 constants in them. And if all of the constants line up properly, then you'll be able to produce a two-distance set. So then you just observe that there's infinitely many cases where these things line up properly. So here's one example of a frame. So the frame is the column vectors. We have 1, 2, 3, 4, 5, 6 vectors in R4. Now, it turns out these are not sitting in R4. They're actually sitting in R3 because the column vectors are all perpendicular to the vector 0, square root of minus the square root of 30, minus the square root of 15, minus 3. So these vectors are really lying in a R3. This frame turns out to be a maximal regular two-distance set summing to 0, but it's not tight. The reason for this is important is up until this paper, there was no known example of a maximum regular two-distance set that was not tight. Every one that was known was automatically tight. That was happening because the constructions were quite elementary, and it automatically made everything tight when you did those constructions. So I was right, there's only about 35 minutes. This is Chase. I hate to tell you, poor Chase, he died last month, but I still love him. So thank you very much for everybody.
Great, so there's a reactions icon you can click. You can click the applause button.